Take a look at this relation. 1 is mapped to 2, 2 is mapped to 4, 3 to 9, and so on. Without having to work out what the numbers 4 to 10 are mapped on, can you tell me what 11 corresponds to? It is 121, because this is the function f(x) equals x squared. How about if I gave you two sets of mappings, both mapped from the domain shown, and I asked you for which term in the domain do both mappings have the same value? You could keep writing out subsequent terms until they both match, and here we're pretty lucky because they match relatively quickly at term 11. Or you could save yourself a lot of time if you knew that the first mapping is denoted by 3x plus 2 and the second is 5x minus 20. Then it is simply a task of equating the two linear functions to yield x equals 11. Hopefully now you are starting to have an idea about why functions are important. Because once you know a function, you automatically know everything about the set of numbers it describes. When does the set hit 0? How fast does it grow? Does it have a maximum or minimum point? A function really is a mathematical description of a pattern. How do we describe a U-shaped object? Using f(x) equals x squared. How about a wave? We use the trigonometric functions sine and cos. So in this video, we'll look at what functions are, the function notation, some new terms, and we'll close with some examples. A function is a special type of relation where each input is related to exactly one output. What does this mean? Visiting our relations from earlier, it means that only one-to-one or many-to-one relations are classed as functions. Note that an output can have different inputs, but each input may only be related to one output. Using a baking analogy, you can think of a function as a recipe. You start off with some ingredients, and it tells you what to do with them to create your end dish. You could start off with one or many ingredients, but in the end, you always end up with one dish. Another way to think about this is to imagine that the function is a machine. Your raw materials are your domain, and your end products are your codomain. The machine follows a pre-programmed set of instructions to process the raw materials, much like how your function is a predefined rule, which you apply onto your inputs to obtain the final product. A function, read f of x, can be denoted in two ways, although we usually use the second method. This simply means that the function f is bringing an object in the domain x into the codomain y. For example, both of these functions, where m and c are constants, are equivalent representations, and they just mean that for a certain input value x, our function yields the result mx plus c. We write it this way because it's convenient for us to remember what our inputs and outputs are, and it shows directly how the input is related to the output. This property may not be the most obvious when you're dealing with one variable only, but in further studies, you'll come across functions having more than one input, for example, f xy equals z. When considering functions, our inputs and outputs are very important. So we have specific names for everything we deal with. You already know what the domain and codomain are. Here, we introduce the object, which is one input selected from our set of possible inputs, the image, which is the output of a specific object, and the range, which is the set of all images generated by our domain. When presented with new information like this, never be afraid to question it and ask, how does this fit in with what I already know? Not just in math, but in any area of life. You learn the best when you take in new information, digest it, and make it your own. I think the best way for me to illustrate the difference is through an example. Using our equation from earlier, f(x) equals 5x minus 20, we define the domain and codomain as the set of all real numbers. Both of them are set by us beforehand, or in other words, before we even start calculating, we first define the base numbers we'll be working with, and then we say, we are only interested in results which are within our codomain. Limiting the results we are interested in becomes more applicable when you only want to deal with positive or negative numbers, and also when you start working with complex numbers and numbers in higher dimensions like coordinates and vectors. Back to the example. Let's input a value x equals 10 into our function. This specific choice of input is called an object. Putting 10 into our function gives the result 30, which is the image of 10. So an object is a specific selection from our domain, and an image is the specific output corresponding to that object. How about the range? Say now we change our domain to the set of numbers between 0 and 10, while leaving the codomain constant. Now our function can only take values between -20 and 30, as you can see, and so we call this its range. That's because the range of a function depends on both the function and its domain. There are three conventional ways to visually represent functions, which are by arrow diagram, ordered pairs, and graph. Note here that when you write out a relation in ordered pairs, the input and output are separated by a comma, and that all the ordered pairs are contained in the set notation. Here are some common functions that you'll be dealing with, so it's a good idea to familiarize yourself with them. That's a linear function, a reciprocal function, a quadratic function, and the modulus function. The modulus is a new operator that you'll be seeing pretty often. The modulus of any number is simply the positive value or absolute value of that number. So the modulus has no effect on positive numbers, and takes the negative value of a negative number to make it positive. Remember, the modulus only ever returns positive values. Before we close, here's a look at some really famous functions in function notation. First, it's Pythagoras' theorem, where the hypotenuse of a right-angled triangle is a function of the lengths of its two sides. Einstein's mass-energy equivalence, which states that the mass is a function of an object's energy, where m equals E over c squared, or rearranging, E equals mc squared. Everybody knows this one, but do you really know what it means? And lastly, the theory of everything, or almost everything, as described by the Standard Model. Basically, this represents physicists' closest explanation of why everything is the way it is. These last two functions have fundamental, far-reaching effects in the world we live in. E equals mc squared altered the course of our history, and the Standard Model, if true, may well alter the course of our future. Find out more about them in the links below. That's all for this video. Remember to stay curious and always follow your dreams. See you in my next video.